Well, last time we left off talking about how we were going to talk about the squeeze theorem. Okay, so this is theorem 9.3, and it's called the squeeze theorem. Some people call it the sandwich theorem. But it's called the squeeze theorem because basically it forces a limit to occur for a function. It basically says if the limit as n approaches infinity of a sub n is equal to L is equal to the limit as n approaches infinity of b sub n, and there exists an integer n such that a sub n is less than c sub n is less than b sub n for all n greater than n. Right now I'll explain this thing in plain English. Then the limit as n approaches infinity of c sub n is equal to L. So right now I'll explain this thing in detail in normal English. Okay, but if the limit of a sub n and the limit of b sub n as n approaches infinity is equal to L, then there exists some integer, capital N, such that if you introduce a function that's between a sub n and b sub n, then its limit itself is going to be a value of L. It's going to be squeezed into it. So let me just give you an example of something like this. Okay, it's not going to be anything too concrete, but just an idea of what it would kind of look like. So let c sub n exist such that we have such that a sub n is less than c sub n. Actually should be less than or equal to. I just realized I didn't write that down. On the main definition, guys, should be less than or equal to. Okay, so both of them should be less than or equal to. So let c sub n exist such that a sub n is less than or equal to c sub n is less than or equal to b sub n. Okay? Let the limit as n approaches infinity of a sub n equal to L, and the limit as n approaches infinity of b sub n equal to L. So we're going to let that exist. Okay? So we're going to assume that there's a function that's less than or equal to b sub n. Okay? So there's three functions here. C sub n is a function that's less than or equal to b sub n, but it's also greater than or equal to a sub n. So it's just a function in between. Okay? If you're kind of saying like, what the heck does that mean? Here's a little tiny picture of maybe what that could look like. Okay? Let's say that here are three functions. Okay, and they're going to meet up right there. Okay? But notice how the red one is bigger than or equal to the blue one, which is bigger than or equal to the green one. You guys see that? So there's three functions: a sub n, b sub n, and c sub n. Okay, I can call this my b sub n, this will be c sub n, and this will be a sub n. Well, yeah, because c sub n has to be in the middle, b sub n should be the bigger one, a sub n should be the smaller one. Okay, and let's assume that their limits, okay, go to L. Now the picture doesn't show that, but the picture is just so you can understand the inequality. But let's assume that their limits go to infinity. Okay? So if I start with this, a sub n less than or equal to c sub n less than or equal to b sub n, and I say let's take the limit of this whole inequality. So I'm going to write limit as n approaches infinity of a sub n must be less than or equal to the limit as n approaches infinity of c sub n, which is less than or equal to the limit as n approaches infinity of b sub n. So I basically just applied a limit to all of them. Okay, you can do that with inequalities. You can add numbers, multiply numbers, subtract, divide. Okay, so I'm just taking the limit of everything. Well, what's the limit as n approaches infinity of a sub n? So I have that in the let statements. So I say let the limit as n approaches infinity of a sub n equal to L. So this is L less than or equal to the limit as n approaches infinity of c sub n less than or equal to, what's the limit as n approaches infinity of b sub n? Also L. So look at the inequality. The limit as n approaches infinity of c sub n has to be bigger than or equal to L, but it has to be less than or equal to L. So what's the only option for it? What does it have to be? So if you look at the limit in the middle, notice how it has to be bigger than or equal to L, but less than or equal to L. It has to be L. It gets squeezed, right? It has no other choice. Okay? So right here I say, so the limit as n approaches infinity of c sub n has to be L. It has no options. It can't be less than L and it can't be bigger than L because it's L on both sides. So it must be L. Okay, it has no choice whatsoever. So they get that idea, the name that they call it, the squeeze theorem. Sometimes you hear it in old like mob movies and stuff. They say put the squeeze on somebody, right? What that basically means is make them do what we want them to do, right? That's what's happening to the middle limit. It has no choice. It's going to become whatever the limits are around it. Okay? So that's what the squeeze theorem is. Okay? Like if you can find a function that can fit in between two other functions and you find that their limits are a specific number, then the middle limit will become the same thing. So we're going to do an example just to kind of show you this. Okay? So I'm not sure what example we left off on. Let me see. We did 1. We did 2. So this is going to be 3. All right. So example 3. So for example 3, we're going to show that c sub n, which is equal to negative 1 to the n, 1 over n factorial, converges, in other words, it has an answer, and find its limit. Now I'm going to put a little hint here. Now this hint is actually something you got to carry on with you, okay? So n to the n is greater than n factorial, which is greater than an exponential, which is greater than a quadratic, which is greater than a linear. I just use the number 2. You could use a 3 or 4, whatever, but
What does it say?
Converges and find its limit. Find its limit. X. But it's very important that you guys know what functions are bigger than what. Okay? Because what we're going to be doing in these series things we're going to do eventually is we're going to do a lot of comparison. And we got to check, okay, this equation is bigger than this equation, or this equation is smaller than that equation. Okay? So notice that right now my function has an n factorial, so I have to pick one of those functions to check it with. Okay, so n factorial is in the middle. 2 to the n is smaller than it. Okay, and n to the n is bigger than it. Now that's just n factorial. Okay, so I got to pick one of those to use. Now I'm going to tell you, never use the n to the n unless it's like life and death. Okay, which never happens. So always pick less than it. Okay, if you can. So I'm going to use 2 to the n to compare. So let me show you what I'm talking about. N factorial is greater than 2 to the n. Okay? N factorial is greater than 2 to the n. 1 over n factorial is less than 1 over 2 to the n. Do you guys agree with that? 1 over 2 is greater than, I'm sorry, what am I saying? 3 is greater than 2. You guys believe me? Right? Is it true that 1/3 is less than 1/2? Yeah. If you flip something, the inequality flips. Okay? Because what once was bigger, if you put it in a denominator, now makes that thing smaller. Right? The bigger the function in the denominator, the smaller the function actually is. Right? But yet, if it's in a numerator, then that function, the bigger the function is, the bigger it is, right? Like there's no choice. It's just bigger. So what I did is, I took my n factorial, which is here, okay, in my original function, and I said, okay, let's compare it just normally to any other function. So I compared it to 2 to the n, and I said, okay, n factorial is bigger than 2 to the n. Now, if I flip it around, 1 over n factorial is less than 1 over 2 to the n. Okay, well, great. I'm trying to build this. A sub n less than c sub n less than b sub n. Okay? Right now, so far, I have that. Okay? Because c sub n, I need it in the middle. All right? So, I'm trying to build that idea. Now, what I have is my c sub n and my b sub n, but I need an a sub n. What would be smaller? Well, this is actually the easy part. You're just going to say negative 1 over 2 to the n. So whatever b sub n is, just do the negative of it. So before I move on, are we okay with what's just happened? All right. So I made a comparison with the n factorial first. I flipped it upside down. So I figured out my c sub n and my b sub n. And then to find a sub n, I just made b sub n negative. All right. So to figure out its limit and to see whether or not it converges, what I'm going to do is I'm going to apply limits to everything. Okay? So the limit as n approaches infinity, I'll answer your question right now. Let me just write this out, is less than the limit as n approaches infinity of 1 over n factorial, which is less than the limit as n goes to infinity of 1 over 2 to the n, right there. So go ahead.
How do you know that you have to use n factorial and 2 to the n?
I use the n factorial because my main function that they gave me, c sub n, has an n factorial in the denominator. So I figured, well, since I'm using an n factorial in the denominator, what function should I compare it with? I can compare n factorial with 2 to the n or n to the n. I mean, you could also compare it with n squared and 2n, but usually you try to stick to the ones next to it. So I said, well, let me compare it to 2 to the n. Because n to the n, that's just it's a volatile type of comparison. You don't really want to go there. So I'm going to compare it with 2 to the n. Now, I know that n factorial is bigger than 2 to the n. But my c sub n doesn't have n factorial in the numerator. It has it in the denominator, right? So I flip it upside down. But when I do that, the inequality flips as well. So 1 over n factorial is less than 1 over 2 to the n. That's when I say, okay, now that I have this piece right here, that matches this. Okay, because my c sub n is 1 over n factorial, right? So that's in the middle. That means that 1 over 2 to the n must be my b sub n. Now, to find your a sub n is the easy part. Just get your b sub n and make it negative.
Wait, how do you know it was c sub n and b sub n?
Well, I know it's c sub n because 1 over n factorial is this right here. Right? I know that's my c sub n. So therefore, 1 over 2 to the n must be my bigger function, my c sub n. I mean, my b sub n, sorry. Okay? And once you have that, again, a sub n is easy. Just get your b sub n and make it negative. So there's your a sub n. Now I'm going to take the limit of all of them. Well, what's the limit of the left side? As n approaches infinity, what's the limit of negative 1 over 2 to the n? That would be 0. Okay. What's the limit of the right side? That's also 0. So what is being forced of the limit of c sub n? It must be 0. It's supposed to, but it will still work without it. It'll still work without it because it actually has no choice. It has to be bigger than 0 but less than 0. So what does it have to be? Well, it has to be 0. There's no other choice, right? It has to be 0. So this is equal to 0. All right. So cool. We know the limit. But remember, c sub n was not just 1 over n factorial, right? C sub n was, we're going to take the limit as n approaches infinity of negative 1 to the n over 1 over, negative 1 to the n times 1 over n factorial. Well, we already know what the limit is for 1 over n factorial, right? So will the negative 1 to the n make any difference if it's a 0?
No.
No, so this is still just 0, right? So the problem says show that it converges. Well, there you go. I just showed that it converges. It gave me an actual numerical answer. And then they say find its limit. Well, I did that at the same time. The limit is 0.
What does convergence mean?
Convergence means that it has an answer to a limit that's not infinity. So it can be a 12, a negative 16, a radical 5. Who cares as long as it's a finite value? Has to just be a something, a decimal, a negative, a positive. I don't care. It just cannot be infinite. So convergence just means that it's not infinite. Divergence means it goes to infinity. What was your question? Or was that the question? Okay.
Just one example, and the theorem itself took up an entire page.
It takes a while. The good news is the sandwich theorem or the squeeze theorem doesn't show up very often in an AP exam, but every once in a while it does. Okay, so are you allowed what?
With our luck,
Oh, yeah, it hasn't come out in a couple years. So, all right. Now, remember how I mentioned that this thing had like a plus, a negative 1 to the n, right? And I said like, well, what's going to happen in that situation with the negative 1 to the n? There's actually a theorem that takes care of that. So that's theorem 9.4. And it's called the absolute value theorem. And it says, if the limit as n approaches infinity of the absolute value of a sub n equals to 0, then the limit as n approaches infinity of a sub n equals to 0. In other words, who cares if we have a negative 1 to the n on the function, like we do above, if its absolute value, so notice this part right here is the absolute value of c sub n. Right? C sub n was negative 1 to the n times 1 over n factorial. Okay? Now, if I get rid of the negative 1 to the n, that means that I'm taking the absolute value. Notice how the thing that I'm pointing at was equal to 0. So the absolute value of c sub n was equal to 0. Therefore, according to the absolute value theorem, then the actual sequence must also be 0. And that's what we found. The actual sequence was also 0. Okay? So remember, for us, c sub n was negative 1 to the n times 1 over n factorial. The absolute value of c sub n would be 1 over n factorial, because the plus or minus doesn't matter. Right? And that's what we found here.
But would the exponent of n on the first integer not matter?
It doesn't matter. The negative 1 to the n, if you're doing the absolute value of it, it doesn't matter because everything comes out positive, right? Now, without the absolute value, yes, it makes a difference because the first one would be negative and the second one would be positive and the third one would be negative. But they're just talking about the limit. They say if you find the limit of the sequence's absolute value and if it equals to 0, then the sequence itself will equal to 0. Now notice it doesn't say if the absolute value of c sub n equals 5, then the actual sequence equals 5. It doesn't say that. This is a very specific theorem. It says if the absolute value of the sequence is 0, so it has to be 0, then the sequence itself will be 0 too. Okay? So if the limit to this thing, to the answer up on top, would have been 7, let's say this wasn't a 0, but let's pretend that it was a 7, then it does not mean that this has to be 7 as well. Okay? The absolute value doesn't tell us that. The absolute value theorem, doesn't tell us that. The absolute value theorem says that if you can show me that the limit of its absolute value is 0, then I can tell you that the sequence itself has a limit of 0 too. Okay? Very specific. So don't ever say, oh, the absolute value is 7, therefore this must be 7 as well. No, you're not using the theorem correctly. The theorem only applies if you get a 0 here, then this must be a 0. Okay? Are we okay with that theorem? All right, so a very specific theorem. The absolute value has to be 0. Okay? So, pattern recognition. So I think we're gonna probably take a little bit extra here. I'm just checking. Yeah, we're not gonna get into the unbounded stuff today, but I might give you some homework, but we'll do that tomorrow. So it'll take us 3 days to get through this. So let me do some pattern recognition with you guys. So example number, that was 4, right? No, 3. So this is gonna be 4. All right, so find the sequence a sub n where the first 5 terms are given. And then, does it converge? In other words, does it have an answer? I don't care what the answer is, but just does it have one? Now, you can find the answer, and that's fine, but again, I don't care if it's a 5 or a negative 7 or whatever. Just tell me, does it converge? So, here are the first 5 terms. 2 4/3, 8/5, 16/7, and 32/9. Think about this. Yeah, it would be 2 over 1. I'll put that there for you. It's a good way to say, like, okay, how am I going to find a pattern? Try to figure out a pattern for the top and the bottom. Let me just give them a couple more seconds here. Try to see if you can figure it out if you haven't yet. All right, so what, you said you had it. What do you think it is? What's your A sub n?
So I put 2 to the m
Okay.
over 2n minus 1.
All right, so that's good. That's exactly what we want. Okay, 2 to the n over 2n minus 1. So there's my A sub n. We found the sequence. Great. And they say, does it converge? So to check convergence, we're going to take a limit. So the limit as n approaches infinity of A sub n is equal to, well, the limit as n approaches infinity of 2 to the n over 2n minus 1. What does that go to? Because notice 2 to the n grows faster than 2n, right?
Yeah.
So if you're going towards infinity, where does this go? Huh?
0.
Not 0, because the top is growing faster. Yeah, that goes to infinity. If the 2 to the n was on the bottom, then it would go to 0, because that would grow faster. This is infinite.
It doesn't converge.
So it does not converge. So does not converge. And that's it. That's all you got to write for that one. Okay, so we had our sequence of 2 to the n over 2n minus 1. And then we have that it does not converge. Now, example 5, this is really quick. It doesn't take a lot of time, okay? I'm just going to give you 3 different sequences, and you're going to tell me if it converges or diverges, okay? So converges or diverges. So here's A sub n. N plus 1 times n squared minus 6. That's one of them. The next one is n squared minus 3n plus 3 over 9n squared minus 25n plus 7. And C sub n, negative n times n plus 2 times n minus 1 over 6 times n squared plus 6n minus 3. So those are 3 of them. So what do you guys think for A? Okay, so it converges to what? to 0. What about the next one? Yeah, that's going to converge to 1/9. What about the last one? Why?
Because it's got a higher power of itself.
So it goes to,
Negative infinity.
yeah, so it goes to negative infinity. Remember, the way you're checking for divergence and convergence is by taking a limit as n approaches infinity and figuring out, does it have an answer? You don't need to know the answer, okay? It doesn't ask you to find it, but when you take the limit, if you find an answer, that means that's a good thing. If you don't, then that's a bad thing, right? So, all right, so let me give you guys a homework for this thing here. Chapter 9. Tomorrow we'll do unbounded and monotonic sequences and stuff like that. So we're at 9. Bless you. All right, let me see what you guys are going to do for this. So 9, 8, 11, 12. I'm just double checking, making sure everything I'm going to give you makes sense. Let's see, 19. 26. 40.
You just have to imagine it like but don't actually sort it out.
Two.
I just thought about the first term.
All right, 87. Okay, so we'll do that tomorrow. So, all right, you guys are going to get a pretty hefty assignment today. Tomorrow it's going to be a lot less, but there's a lot that gets covered in the homework. So I'll give you guys, when we finish the lesson tomorrow, I'll give you guys some time just to work in class, okay? I don't think it'll take us that long to finish up tomorrow. So it's going to be page 604, numbers 1 through 8, 11, 12, 19 to 26, 29 through 40, and 45 to 52, and 73 to 79. So large assignment. I do apologize for that, but it's all based on convergence, finding sequences that converge or diverge, using pattern recognition to figure out the sequences, and then figuring out those converge or diverge. So it's a lot of that stuff.